welcome everybody to this talk. What better topic to address than imprecision itself in this series of talks on imprecise probabilities, and then in particular imprecision in probability theory. Now, before I start, and this is something I typically do, is I want to mention a number of people that I've been working with, that I've been learning from, that I've been talking to, and that have influenced my views on this topic. And I won't name them explicitly, but at least here is a Hall of Fame gallery of the people that I'm really indebted to intellectually. There's a few other people that are not on the list, but they will be mentioned later on in the talk. So if you're not there, please don't be disappointed. Your chance will come. So this is about imprecision, and I have to say that imprecision comes in many forms, in many guises. So the most simple form of imprecision is as a set. Yeah, rather than a single value, we give a set of values, set of possible values for something that we think exists. But it has very many other forms as well. So for instance, when we talk about in functional analysis, the effect of imprecision is that our functionals become nonlinear. So it manifests itself also as nonlinearity. In decision making and in preference relation, it manifests itself as indecision or as incomparability. And then if we go to logic and inference, it manifests itself as incompleteness. So these are all forms of imprecision, manifestations of imprecision. And what you'll have noticed is that in order to describe these things, I need little particles that or little phrases that are negative, like non-linearity, imprecision, indecision, incompleteness, incomparability, which seems to suggest that imprecision is negative, is something negative. And what I'd like to try and at least convince you of by giving a number of examples today is that it is not always a negative thing. It can also be helpful. So that is today's topic. And let me begin in a very simple manner by starting with the basics. So I'll begin with probability intervals. So let's assume that we have some experiment with a set of possible outcomes that is omega, and we consider an event a subset of that set of possible outcomes. And the basic idea, I think, in probability, or imprecise probability, is that rather than give a single probability for that event, we're going to give a set of possible values for that probability, and that set is going to be a closed interval with a lower bound, the lower probability of A, and an upper bound, the upper probability of A, which is, of course, a subinterval of the unit interval. So, well, it's not very interesting at this point, but it becomes more interesting when we look at another event, let's say the event B, and assume that for this event, we've also specified a lower probability and an upper probability, so specified a range of possible values for the probability of that event. And then what makes this interesting is that we can now start wondering about doing inferences with the information that we have, or starting from the information that we have. And in this case, for instance, ask ourselves what is going to be the probability, or what is the probability, or what are the bounds on the probability of, for instance, the intersection of A and B. So for the probability that A and B occur together. Now, in order to solve this problem, it's in a way very natural to look at the constituents of these two events. So the partition of 4 events that exists as a result of where A and B are, and to each of these constituents we can assign a probability. So B for the intersection, beta for the intersection, alpha for A minus B, gamma for B minus A, and then delta for everything that is not in A or B. And of course, because these parameters, these things are themselves probabilities, they have to satisfy a number of constraints. They have to sum to 1. They have to be non-negative. And of course, the probability of A is the sum of alpha and beta. The probability of B is the sum of beta and gamma, and these must satisfy the constraints that we impose by specifying lower and upper probabilities for the events A and for the event B. So what we see here then is that we end up with a linear programming problem under a number of constraints. So we have to maximize, for instance, if we want to find the lower bound on the probability of the intersection, we have to minimize beta under these constraints. And if we want to find the upper probability, we have to maximize beta under these constraints. And so if we do that, if we solve the problem, then we end up with what is known as the Boole-Frichet bounds for the probability. So this is a problem that has been considered quite a long time ago by Boole and more recently by Frichet. Why do I mention this? Because what it makes us see is that, in effect, by specifying these bounds on the probabilities of A and B, what we're actually doing is in fact imposing bounds on probabilities, bounds on the probabilities in this case of alpha, beta, gamma, and delta. And so what we're doing is then we see that specifying lower and upper probabilities for events allows us to consider or to come to the notion of a Credal set. So as a result of specifying lower and upper probabilities, we look at all the possible probability measures that are compatible with these bounds. And of course, this is going to be a closed and a convex set because of the setup of the problem. So a closed and convex set of probability measures that I will denote by this script. And that is our definition for a Credal set, just a closed and convex set of probability measures. So once we have that set of probability measures, so the set of all the probabilities that satisfy the bounds, then we can do inference in a sense. We can now, for any other event C, for instance, for the intersection of A and B in the example, we can now look at the bounds that this set creates on the probability of the event C. So for each of the probabilities in our Credal set, we will calculate the probability of C and then take the smallest and the largest value, just thus characterizing the interval of possible values. So this is a notion of inference. And the basic idea behind it is the notion of a Credal set or a set of probabilities that is at this point closed and convex. Later on, I will also show how we can let go of the convexity and closedness condition, but that is for later. So at this point, what we see is that if we give lower and upper bounds on probabilities, we get to the notion of a Credal set. But it turns out that probabilities are not enough. And this brings me to the notion of expectation intervals rather than probability intervals. Now, in order to explain this, I'll look at the example, a very simple example that will be very instrumental and very useful in what I'm going to try to say here. I'm looking at the example of an experiment with three possible outcomes, A, B, and C. And so I'm going to consider not just probabilities of events, but I'm also going to look at expectations of functions here. So functions on this possibility space. So this means that any function on this space omega is completely characterized by the values that it assumes in A, in B, and in C. So there are, in fact, three numbers that determine such a function. And of course, I can just represent those three numbers that triple in a three-dimensional space. And so I've drawn or sketched this three-dimensional space here with the axis A direction, the B direction, and the C direction. Yeah. So any function on this space can be interpreted as a sort of unknown reward. If I don't know what the outcome of the experiment is, I don't know the value of the function, and therefore the value is uncertain. So we could call this a random variable, or we could call it a gamble. I'll call it a gamble in this talk. So an uncertain reward that you would get. So assume that it is expressed in terms of some linear utility, if you want. So these three possible values, alpha, beta, and gamma, constitute a point. So any gamble, any function is going to be a point in this space. And we have, of course, three very special points. The first one is this one. So this you could call this the first unit vector. And that is, of course, the representation for the indicator of the set A, that is 1 if A occurs and 0 if A doesn't occur. And similarly for the other unit vectors in this space, so the indicator of B is here, and the indicator of the set, or the event C, is there. And then, of course, it's easy to see that any point in this space is just a linear combination of these three unit vectors. So any gamble can be written as a linear combination of these three. This as a bit of preparation of what is going to come next. Now, a probability in this space can be completely determined by a probability mass function, and a probability mass function, of course, is also a function in this space. So it's also a point in this three-dimensional space. And of course, it has special constraints because it must be non-negative and it must sum to 1. So this means that the probability mass functions lie on this triangle that is spanned by the three unit vectors. And of course, we can, if we can just represent this in the plane of the transparency here, or of the slide, then this is what you see here is the probability simplex with the 3 points A, B, and C represented here. And any point in this simplex just represents a single probability measure or a single probability mass function. So any point here. Now the probability of A, for instance, if this is the point that we have, then the probability of A is just the distance from that point to the opposing side of A, so this distance. So the probability of A is indicated on this axis here. And similarly for the probability of B, which is here, and for the probability of C, which is here. Now this means that, for instance, if I look at the line, this blue line here, this is the set of all the mass functions for which the probability of A is 1/2. And this line here is the set of all the probability mass functions for which the probability is 0.2. And if I look at the region that is between those two lines, that is a Credal set, a convex closed set, and it is the set of all probability mass functions that correspond to the specification of a lower and an upper probability of A as given here. Similarly, we can do the same thing for the probability of B, and something similar for the probability of C. So I'm claiming that these are all the probabilities that, or lower and upper probabilities that I can specify, particularly because if I look at the probability of other events, such as the probability of the union of A and B, that is going to be related to the probability of C. So there's the idea is that by specifying bounds on probabilities, these are all the possibilities that I have. And so in general, I will have, if I specify bounds on probabilities in this space, I will end up with a region that is a convex closed set. It's a convex closed polytope. But it is very special in the sense that the sides of this Credal set are always parallel to the edges of the simplex itself, of the probability simplex itself. So what we see is that by specifying probabilities or bounds on probabilities in this way, we only end up, or we end up with a very special type of Credal sets. Normally, those Credal sets for which the sides are parallel to the sides of the simplex. If we want to describe more general sets, then we need to leave the language of events, and we need to go to a more complicated language. We need to go to expectations. So not just probabilities and events, but expectations and variables or gambles. The reason is that if we want to have lines that are not parallel to the sides, then we need to rotate them a bit. And that means that if we rotate these vectors, then what we do is we take certain linear combinations of these vectors and thus end up with gambles. That is the basic and very simple idea behind this. So let me give an example of this. Here I have drawn two lines that are not parallel to the sides of the simplex. This one here in the middle is the line where the probability of B is equal to the probability of C. And I can express this in terms of an expectation as the expectation of the difference between the indicator of C and the indicator of B. So a particular linear combination of those vectors is 0. And this line, also not parallel to the sides of the simplex, is the expectation of the difference of the indicator of C minus 3 times the indicator of B is equal to 0. In other words, the probability of C is 3 times the probability of B. And the region between these two is then a region that is whose sides are not parallel to the sides of the simplex. So we see that what we see then is that in order to specify very general Credal sets that do not have this restriction of being having sides that are parallel to the sides of the simplex, we need to work with expectations rather than with probabilities only. So this is why when we work with imprecise probabilities, we typically do not only impose bounds on probabilities, but we also impose bounds on the expectations of certain gambles. And this brings us to a very simple but very powerful idea that I can summarize in the following slide. Suppose we start with a number of gambles for which we have bounds on the expectations. So we have lower and upper bounds on their expectations. I will call that an assessment. This is something we start out with. This is a partial probability specification, if you want. What we can then do is look at the corresponding set of probabilities that is compatible with this bounds. And we take all of them. So we take the largest possible set that is compatible with this bound. It's going to be a convex closed set. So it's going to be a Credal set. And then once we have this Credal set, we can just take any gamble and for any gamble, calculate the expectation for all the probabilities in that set. That's going to be a convex closed interval that is completely characterized by its lower and its upper bounds. So what have we just been doing? We've been doing conservative inference. We've started with a number of assessments, and we've inferred from those assessments the most conservative bounds on other gambles, on other, or for the expectation of other gambles and for the probability of other events. And I think that this idea that working with partial probability specifications leads to a notion of conservative inference was first considered by Bruno De Finetti, and I think also taken to a logical conclusion and studied in great detail by Peter Waller. Okay, so now we see that we have a Credal set, and that if we have this Credal set, we can derive from this a notion of a lower and an upper expectation as a lower envelope and an upper envelope of that Credal set. And this brings us to a more general notion. Now we can leave the notion of Credal sets behind and start looking at the notion of lower and upper expectations by themselves, not as derived from Credal sets, but as notions that have a right of existence on their own. And so this leads us to what is typically defined as a lower expectation in the field. It's a functional, something that maps gambles to real numbers that satisfies a number of axioms. And you can easily prove these axioms from the special case that they are derived from a Credal set. So for instance, this is the super additivity condition that says that the expectation of sum dominates the sum of the lower expectations. And there is also a homogeneity condition that tells us that we can take positive constants out of the expectation of the lower expectation of the weight. We have similar properties for upper expectations. And it's easy to see that if you realize that there is a sort of relationship between lower and upper expectations that is called the conjugacy relationship, that says that the upper expectation of a gamble is minus the lower expectation of minus the gamble. The fact that this expectation, that this relation exists is an immediate consequence of the idea that they are derived from lower envelopes. So you see that the minimum of a minus, if I take the minus side, this turns into minus the maximum. And so this is where this relationship comes from. If a lower and an upper expectation coincide with each other, then we get the notion of an expectation, and this is just a linear function. So if we now study these lower and upper expectations as interesting objects by themselves, not just as being justified as lower envelopes of linear expectations, then this leads to a very interesting and beautiful mathematical theory that Matthias Trefas and I studied in some detail in a book that we called Lower Previsions, where previsions is just another word for expectations in this context. And so we studied in quite some detail the mathematical structure that arises if you look at these objects, these lower and upper expectations in their own right. And so what you see there is that, initially, I wanted to give an example of this to illustrate it, but I found that I don't have time enough to do that, so I'll have to do that on another occasion. But yeah, there's lots of examples in the book, and if you want to go and look, then you'll definitely find them there, to show that there is this beautiful mathematical landscape of functionals that are called lower and upper expectations, that have a lot of interesting and rich mathematical structure by themselves. And the expectations are very special cases of them. And you can see that the special properties that expectations have, you can place them in this larger mathematical landscape, and see where these properties come from, but also see that they are just special cases of something that is mathematically quite beautiful and very rich. So that is one advantage of imprecision. It allows us to embed the existing theory in a much richer mathematical structure. And that is one initial example of imprecision, I would say. Okay, now, once we have these lower and upper expectations, let's look at decision-making, given lower and upper expectations. So in decision-making, what we do, and in order to explain this example, I'll look now at the possibility space with two possible outcomes, because that allows me to make very simple pictures. And so I have two possible outcomes in my possibility space, A and B. And so all the gambles on this possibility space can be represented in a two-dimensional space. So any point in this two-dimensional space represents a gamble, with the value in A being the first coordinate and the value in B being the second coordinate. And so I have a gamble F in this space, so a point in this space. And the question now is, so this is also an uncertain reward. It's because I don't know the outcome of the experiment. I don't know the value of the gamble, so I don't know the value that this gamble will take. And the question then is, when will I prefer this uncertain reward to the status quo, to the zero gamble? And I express this by saying that the gamble is strictly preferred to zero. Now, if my expectation were precise, typically what we would do is we would accept such a gamble or strictly prefer it to zero if it is a strictly positive gamble, so if it is in this first orthant here, or if its expectation itself would be positive, because if I expect the gamble to be positive, I will prefer it to zero. Now, I no longer have a precise expectation. I have a set of precise expectations, or a Credal set, if you want. And so I now want this inequality to be true for all of these candidate expectations in that set. And this, of course, is equivalent to requiring that the lower expectation of the gamble should be strictly positive. So when do I, using this lower expectation model, when do I prefer a gamble to zero? When its lower expectation is strictly positive. Then if I assume that I have a linear utility, which I have been assuming from the outset, then I can extend this preference relation of gambles preferred to zero to one gamble preferred to another gamble, if and only if the difference between the first and the second is preferred to zero. Yeah, so I can derive more interesting relationships from the relationship of gambles with respect to zero. Now, if I replace in this identity, if I replace G with zero, then the converse relationship, namely, or the inverse relationship, namely that 0 is preferred to the gamble f, then can be easily found by replacing g with 0 in this expression. And so I find that minus f must be greater than 0. And if I do all the maths, then I find that this is equivalent to the upper expectation of the gamble being strictly negative, or the gamble itself being negative. So these are two conditions for f being preferred to 0 or 0 being preferred to f. Now it follows from the properties of a lower expectation that the set of all the gambles with a positive lower expectation is a convex cone. It's depicted by the green area in this figure here. And then the gambles for which the upper expectation is negative is another convex cone. In fact, it is the mirror image of this convex cone using this through the origin. Yeah. So what you do is you go to, because of this relationship here, the gambles that are in the blue region are minus the gambles that are in the green region. But what I want to point out here is that, so this relationship between gambles and 0 is not complete. In fact, there is this white region. So any point in this white region, for any gamble in this white region, we see that it is neither preferred to 0 or the other way around, that 0 is not preferred to this gamble. So there is for these gambles, so the decision between 0 and the gamble f, accepting the gamble 0 or accepting the gamble f, this decision is not made here. There is indecision in this model. And so the white region is the region of indecision. And so what we see is that if we allow for imprecision, then indecision manifests itself in this very structured way. Of course, there would be no indecision if both these regions were, so if the white region were to disappear, and this of course happens if they touch each other, the blue and the green region, and then of course they are the borders of a hyperplane. Also, the hyperplane it then becomes their border in this case. And so, of course, these hyperplanes, the red line that you see here, all the red lines that I can make to fit within this white region will then, of course, be all the precise expectations, or correspond to all the precise expectations that constitute the Credal set that corresponds to this lower and upper expectation operator. So this is the idea that if we do decision making and allow for imprecision, then this leads to indecision. And so indecision, and this is a manifestation of the imprecision of the model, or vice versa. Now we can take this abstraction step one step further and look at the idea of when is a gamble strictly preferred to 0, and use this to define elementary statements. So we will call a gamble desirable if it is strictly preferred to 0. And then we can look at a sort of a logic of desirability that is based on elementary statements that I will represent by this symbol. So a sort of entailment symbol that says that the gamble f is desirable. I'm going to just denote this in this way. And then based on what we've seen for lower and upper expectations and the notion of preference to the 0 gamble that I've discussed there, we come to a number of basic axioms for the logic that governs these simple statements of desirability. The first one is that, of course, 0 is not desirable because 0 is not strictly preferred to itself. If we have a positive gamble, then it must be desirable. So the first orthant here in this space consists of the gambles that are desirable. And then the last two of these axioms just represent the fact that the desirable gambles, the ones that are preferred to 0, constitute a convex stone. So it's closed under addition and closed under multiplication with a positive gamble. So this tells us that we have a logic of desirability. And then with this logic, there corresponds a notion of inference, of deduction. And so the sets that are deductively closed will be called what we call the coherent sets of desirable gambles. So this is the idea that this type of inference is governed, or there is a logic behind this type of inference and behind the type of conservative inference that I've been discussing before. It's easy to see that the logic behind desirable gambles, so the logic I've been describing in these axioms, underlies all of probability theory, at least the finitary parts that do not rely on any continuity properties. In the sense that if I have a notion of desirability and a set of desirable gambles, then I can derive from that an over expectation functional as a sort of supremum over all the values alpha for which f minus alpha is desirable. You can extend this to a notion of a conditional expectation also. A conditional expectation then for a gamble f will be the set of all the alpha for which the called off gamble f minus alpha, the gamble that is f minus alpha if A occurs and is 0 if A does not occur. So the price in a sense for this called off gamble. And this is how you condition, and you can show that Bayes' rule when we have precise models rather than imprecise models. So when this expectation is precise, then you can show that the Bayes' rule follows from this. So it seems that, or you can show that Bayes' rule, at least in this interpretation, is part of this logic and is therefore also deductive. It's deductive property of that logic, or a deductive notion in that logic. So what does this tell us? That if we allow for imprecision, then this shows, it lays bare the conservative inference mechanism that lies behind probabilistic reasoning. And so this is hidden if you only look at precise models that are specified on, say, on sigma fields or on fields of events. Then this inference mechanism is somehow hidden. And once you allow for imprecision and for partial probability specification, then you can start to see that there is indeed this conservative inference mechanism, this logic that underlies all this type of reasoning. And it's a very simple inference mechanism. We can make this a bit more complicated. The idea that I've described here is the idea of binary choice. The relations that I've been describing are relations that, let me go back, are binary relations where we compare a gamble to the zero gamble, or we compare one gamble to another. So this is a binary notion of preference. You can extend this binary notion of preference to non-binary notions of preference, and that is what is typically done by looking at choice functions. Now, recall that I just said that binary choice is governed by a logic of desirable gambles, and it turns out, and this is something that we've shown recently, that you can get to non-binary choice and choice functions and the theory behind choice functions by simply adding another extra idea or another axiom, if you want. And so the idea is very simple. If you look at these axioms here, so the axioms behind binary choice, what you're actually doing in this inference mechanism is only look at ands of desirability statements. So if you have a set of desirable gambles, this means that every gamble in that set is desirable. So you take a conjunction of desirability statements, of simple desirability statements. If you also want to allow for disjunctions of desirability statements, that is what allows you to get to non-binary choice, the theory of choice functions. The idea is quite simple. You will add an axiom that says that if I have an OR of simple desirability statements, then this will tell me This will introduce a new notion, namely the desirability of a set of gambles. So a desirable set will be a set for which at least one of the gambles is desirable. And in this way, you not only get and statements, but also or statements for gambles. Turns out that, and this is also something that we've proved quite recently, that this is exactly equivalent, so isomorphic, if you want, to doing a propositional logic with only with statements of the type F is desirable. So this type of logic is completely governed by that. It is a one-to-one relationship between these two things. And so essentially what we then see is that once we have this theory and these results, you can also prove representation results. So these are results that that allow us to represent the deductively closed inferences in this more complicated logic in terms of representing things. So and the representation results tells us that we have a kind of Levi's e-admissibility. So all these results can be written as e-admissibility choices, where what we do in Levi's case is we use precise probabilities as the representing sets. Well, these precise probabilities are in this more general framework replaced by coherent sets of desirable gambles. So those are the most basic models instead of probability measures. Also, and this is something I pointed out before, the sets of these probabilities are no longer necessarily closed or convex, or the sets of these coherent sets of desirable gambles are no longer necessarily closed or convex. And we can add extra axioms to this to these axioms that we have here, and then we get to extra structure, and for instance, get to a notion of admissibility where these coherent sets are just replaced by sets of probabilities. So what I want to say with this is that essentially, if you allow for imprecision, then you can also lay bare the link that there is between probabilistic reasoning on the one hand, using these very simple desirability statements, and very powerful representation results that exist in choice theory. And this is, of course, work that was initiated by Teddy Seidenfeld, and this is work that I've done together with Jasper and with Arthur de Bock. Right, so this was all quite simple still. Let me check the time at this point. Okay, this is all quite simple still. I want to make it a little bit more complicated by looking at stochastic processes. So a stochastic process is just a sequence of variables, a sequence of things whose outcome is uncertain. And I have such a variable, something whose outcome is uncertain for a number of times. So for time 1, for time 2, for time 3, and so on. So I have this infinite sequence of variables. And for simplicity, I'm going to assume that these variables can only assume the values 0 and 1, just as an example. So I have a number of values of variables that can assume the value of 0 and 1. So at time 1, I observe 0 or 1. At time 2, I observe 0 or 1. At time 3, I observe 0 and 1. So in the end, all the possible outcomes are strings of zeros and ones, and I can represent these strings of zeros and ones in a tree, in what we call an event tree. So here is time 0. Time 0, I can have a 0 and a 1, and this is represented by this small tree here. Then once I've observed 1, for instance, and at the second time instant, I can observe 0 or 1, so I get this other small tree, and so on. Yeah? So all the possible finite strings of zeros and ones are points in this probability tree, so nodes in this probability tree, and I will call these situations. So finite strings of states in this tree, and then if I go on indefinitely, I will get to an infinite string of zeros and ones, and of course that is a path in this infinite probability tree. Okay, and then what we can do at this point is, so this is just an event tree. Now I'm going to start attaching probabilities to this tree. And the idea is that after each outcome, so in each possible situation in the tree, so after each sequence of outcomes, I have some idea, some beliefs, some probability model for the next outcome. And I'm going to represent this by these green arcs here. So for instance, here, before anything happens, I have some beliefs about what the next outcome is going to be, either a 0 and a 1, and I'm going to represent this by a precise mass function or a precise probability model. After observing 1, I get another precise mass function for the next outcome, which can be either 0 or 1. And because I have this model in the situation 1, I will denote it by P sub 1. And then for instance, here in 1, 0, I have another model P 1, 0 that gives me my beliefs about the next outcome, which can be 0 or 1. So the idea is that if I attach to each of the situations in this tree a model about a local model, which means a model about what's going to happen immediately afterwards, then I get to what we call a probability tree. And in order to distinguish it from something that will come later, I will call it a precise probability tree. So that is, in a way, a way to describe a stochastic process by using a precise probability tree. Now, what is an imprecise probability tree? It's very simple. What I'm going to do is I'm going to replace all these precise local models by imprecise ones. So one way to do that is by replacing the local mass function by a lower expectation operator in each of the situations. Or I could replace it by a set of desirable gambles in each of these. So a cone, a convex cone of desirable gambles in each of these situations. Or, and this is what I'm going to do here, I can replace it by a set, a closed convex set or a Credal set of probability mass functions in each of the situations. So this is an imprecise probability tree. In each situation, I have a set, a convex closed set of probability mass functions for what is going to happen immediately afterwards. Now, what is the interpretation of such an imprecise probability tree? Well, the idea is quite simple. In each of the situations, I have a set of possible candidate probability models, local probability models. So what I'm going to do is, I'm going to derive a precise probability model for this by, in each situation, selecting just one single probability model, one single mass function from the set of available probability mass functions. And I can do that, of course, in an infinite number of ways. And so what we see is that an imprecise probability tree corresponds to an infinity of precise probability trees. I will call these compatible precise probability trees. And by just choosing in each of the possible situations, one of the available candidates, precise candidate models. So what we see is then that an imprecise probability tree is in fact equivalent to a set of precise probability trees. Now, how do we do inference in such an imprecise probability tree? Well, the idea should now be obvious. We look at all the compatible precise trees. We do in each of these compatible precise trees, we do the inference. That will give us a number, typically, because we calculate an expectation or a probability. That is what we mean by an inference. And then we get a number. And then, of course, by ranging over all the compatible trees, we will get a convex closed set of those numbers, and that is completely determined by its minimum and its maximum. So this is, in principle, how you could do inference in such an imprecise probability tree. Now, first of all, doing such inferences in a precise tree, in a general precise tree, is already going to be very complicated. It's also already going to be, generally speaking, of exponential complexity because you need to record all the local probability models. So it's going to be quite complicated. Adding imprecision to this picture makes it even more complicated because now for each of these, so you have to do the calculation for an infinity of for many models that are compatible, so precise models that are compatible. And of course, the number of models increases exponentially as we go along. So we get like a double exponential complexity. There's already an exponential complexity for doing the calculations in the precise tree, and then precision adds to this complexity. So it seems hopeless. Well, it's not really hopeless. But before I go on, I just want to mention here, before I show that it's not entirely hopeless, I'm going to mention here that this idea of attaching imprecise probability models to the nodes of a tree is in fact a very natural way of establishing a connection between, on the one hand, the measure theoretic probability, and on the other hand, the game theoretic probability that Glenn Schaefer and Volodya Vovk have been studying. So allowing for imprecision allows us also to establish a connection between the notion that we have in precise probability, measure theoretic probability theory, and on the other hand, game theoretic probabilities. Okay, so why is it not entirely hopeless? Well, in order to see this, we have to look at the notion of imprecise Markov chains. On the left-hand side here, you see a general imprecise probability tree with the local models. What I'm going to do now is I'm only going to consider imprecise probability trees that satisfy a Markov condition. The Markov condition is here on the right. It says that the local Credal set, after observing the variables x1 through xn, only depends on the last variable. So the previous outcomes are not important in determining that set, which means that here on the left-hand side, the picture simplifies somewhat. So this tells me that because here and here and here, the last outcome was a 1, I will have the same model. And because here and here and here, the last outcome was a 0, I will have the same model for those 3 nodes as well. So there's an important simplification there. And we call this simplification the Markov condition. And due to this Markov condition, you can show that many of the inferences that are done in an imprecise Markov chain become polynomial in complexity and are no longer exponential in complexity. And that is very interesting. It's very similar in precise Markov chains as well, by the way. So instead of having an exponential complexity and doing calculations in the tree, you reduce it to a polynomial complexity by the Markov condition in the precise case as well. But the interesting thing is that this also happens in the imprecise case. Now, what makes this interesting is the fact that you have to remember that in this tree, in this imprecise Markov chain, if you want, that the interpretation of that thing is that this is equivalent to considering a number, an infinite number of compatible precise trees. Yeah. So what we do is in each of these situations, we will pick one model in the available set. So here in this situation and in this situation, I will pick a model in the set M1. But there is nothing that says that in this situation and in this situation, I have to pick the same element of M1. I can pick another element in this situation, one element in this situation, and another element in this situation. So this means that the compatible precise probability trees need no longer be Markov chains. They need not have the precise Markov property. In other words, for an imprecise Markov chain, so where that satisfies this, the underlying precise models are not necessarily Markov. Now, for those models that are not necessarily Markov, the inferences will be very complex. They will typically be of very high, even exponential complexity, typically. But what we see is that we can do calculations on the bounds of these models. So because they are inside these sets, we can do calculations on the bounds for which the complexity becomes polynomial, becomes much simpler. And that is a very powerful idea. The idea that by allowing for imprecision, we can efficiently calculate conservative bounds on the behavior of the precise stochastic processes that need not be Markov. And so doing the calculations on those processes themselves would be very complicated, but we can do conservative bounds calculations that are much less complicated. So this was an idea that I realized was there quite some time ago, and that more recently has been taken up in the context of both discrete and continuous time Markov chains by Jasper de Bock, by Alexander Reger, and by Thomas Krak in the context of lumping. The idea is very simple. Once you get to think of it, of course, the idea is that suppose that you have a precise Markov chain. So ideally, it would be easy to work with that and to do calculations with that. But suppose that the state space is very large. Now, because of this very large state space, calculations become quite complicated and quite computationally complex. And so it's difficult to do them in a reasonable amount of time. Let's assume that that is the case. So what we typically do then, when we work with precise Markov chains, is we lump number of states together in order to reduce the size of the state space. The problem with this is that, generally speaking, the resulting process that specifies how we go from one lumped state to another lumped state is no longer necessarily Markov. But it is, we can specify bounds on those processes that are and that do satisfy the Markov condition, and then the idea becomes very simple. We can no longer precisely describe this process because it's no longer a Markov chain, and therefore it will be much more complex to do calculations with it. But it is, in a sense, a part of an imprecise Markov chain for which we can do the calculations and therefore can give useful conservative bounds. And this brings me to the following idea, and I think this is quite important. It is an interplay between a number of notions. First of all, there's a notion of accuracy and the somewhat incompatible notion of precision. It is very hard to have an accurate model, a model that is correct in a sense, that is also precise, completely precise. And these are, because it's very difficult to give a precise number for something and have it at the same time be correct. So we can keep accuracy in a conservative way by decreasing the precision and becoming more imprecise. The idea will then be that my imprecise model will contain as a subset my the real model. And so I in a conservative way, I'm still accurate in that sense, but I'm no longer precise. So there is this one tension, the tension between accuracy and precision on the one hand. There's another tension that exists between accuracy and simplicity. Typically, for a model to be accurate, it will typically, for reasonable and for realistic situations and processes that we want to model, it will typically be quite complex. So there's this other tension between accuracy on the one hand and simplicity on the other hand. Yeah. And so what I've just shown or indicated is that that if you allow for imprecision, then you can somehow alleviate this tension between accuracy and simplicity. So by becoming more imprecise, you can keep the accuracy in a conservative sense. And what we see is that you can also reduce the complexity, the computational complexity of doing the calculations that you still want to be accurate. So this allowing for imprecision here is a way to alleviate the tension between accuracy and simplicity. Now I'm also going to, as a last example, and then I'm going to finish, give you a similar argument or a similar. This idea comes back when we study algorithmic randomness. In this endeavor, the endeavor of algorithmic randomness, what we look at is a sequence of zeros and ones for which we ask ourselves the question, is this sequence of zeros and ones, is it random? Now, typically what you need in order to make this a reasonable notion is you need to specify, again, a probability tree. So you have, again, this is a sequence of 0 and 1s. You can imagine that this is the outcome of a stochastic process, the path of a stochastic process. And so you have this event tree, and in each of the nodes of the event tree, you have a precise probability model. And once you have such a precise probability model, once you have a precise probability tree, then there is a very a standard way of defining whether a sequence is random with respect to this precise probability tree. There's two ways of defining that. One goes through randomness tests, and another one goes through the notion of martingales or super martingales. Now, what I and Jasper did some time ago is we extended this idea to allow for imprecision in the probability tree. So we also have a definition for randomness in an imprecise probability tree. And together with Floris, who is here, Floris Perciot, we showed that there's also two ways of defining this, using, on the one hand, randomness tests, and on the other hand, using super martingales. Now, what is interesting here is that if you have something that is random for a probability tree, if you have a sequence of zeros and ones that is random for a probability tree that is more precise, then it automatically will also be random for a probability tree that is less precise. Yeah? So randomness is preserved by going to a more imprecise model. So again, here you have this notion that accuracy becomes easier if you go to a more imprecise model, not the other way around. And there are important theorems that show us that this is not the case in the other way. So it's not necessary. So for any less precise probability tree of a path is random, there will always be paths that are not random for the more precise ones. That is one of the results that we proved. Now this is interesting because if we start from a precise probability tree and a path that is random for such a precise probability tree, what we could do is we could collect all these precise mass functions into a single set that I call N. Yeah? And this is an imprecise model. And then of course, this new tree will, in each of the nodes, will include the model for the precise tree that we started out from. So this tree will be less precise than the previous one. And so our path will also be random for this tree. But this tree is much simpler in the sense that it is what we call stationary. It has the same model in all the nodes. And so it's a much, from a parametric point of view, a much simpler model. Now, suppose that we want to learn this model, then it's going to be much easier to learn this stationary model rather than the non-stationary model, where we need to learn an infinite number of values, an infinite number of probabilities. So here too, what we see is that we can replace the study of a non-stationary precise model by something that is stationary and therefore simpler, but that then must necessarily become imprecise. And again, we have in this context the fact that if we allow for imprecision, we can remain accurate in a conservative sense and come up with a simpler model. In summary then, what I've tried to show you by using a number of examples is that if we allow for imprecision in probability theory, it will help us deal systematically and honestly with indecision and with incompleteness. It will allow us to see this precise special case in a much wider and a structured mathematical perspective, in a wider context. It will allow us to identify and to use the logic and the conservative inference mechanisms that are behind probabilistic reasoning. it provides a natural link between measure-theoretic and game-theoretic probability. And it allows us to look at and to use simpler and more conservative models that are computationally more tractable. These are just a few of the examples that I wanted to give and of the advantages of using imprecision that I wanted to give. I've only been able to scratch the surface. I started to realize while doing this talk. And so perhaps one result of this is that I'm considering perhaps writing a small book or a huge article on this idea. And you have been my test audience. I'm happy to say that this is now the end of my talk, and I'd be very happy to answer your questions.